So welcome to the first theoretical astrophysics seminar of the spring semester. And it's really nice to have here Davide Gerosa as the first speaker. So Davide works on different aspects of the dynamics of compact binaries and how especially you can use gravitational waves to infer the properties of binaries of stellar mass black holes and well as other types of compact objects. Lots linked to the work that you can do with the LIGO data, but not only. He has a wide range of interests also in general in understanding the relativistic dynamics of physical objects. He has worked a lot on eccentricity and spin, how to infer them from the data, so at the boundary between data and the modeling part, including also modern techniques like machine learning, which is what he is going to include in his talk today. He started out his career in Milan, in my hometown, actually. And then from there, he went to Cambridge for a PhD, so at Dump. He got his PhD in 2016. Then after that, he moved to the US. He got the NASA Einstein Fellowship to work at Caltech, where he has been for 2 years or so. And
almost three.
3 years. Then after that, he moved to the UK, where he became an assistant professor in Birmingham, where there is a big center for gravitational wave science. And then after that, he came back to Italy with a very prestigious ERC grant, and he got an associate professorship with that. This was in 2021, so not long ago. And he has a lot of people, a number of people now working together with him to understand everything about gravitational wave source. So that's the topic of today. So deep learning emulators for gravitational wave population.
Thanks all for being here. Thanks for inviting me, and thanks Lucio for the kind introduction that I'm not sure I deserve. So this is work done, well, mostly by my finishing grad student, Matt Mold, who's about to start a postdoc at MIT, and in collaboration with Steve Taylor from Vanderbilt University. And so what we were trying to do is, as I'll try to argue today, is to design at least a prototype of a full comparison between gravitational wave data and state-of-the-art astrophysical prediction. And we think that you do need to throw some deep learning into the blender to make this work. And hopefully this will clarify what I mean. All right, so this whole business started from the, what I call the gravitational wave revolution that, in 2015-16, really kickstarted a new research strand on, entirely. This is the first thing, you've seen this plot a million times, but this is the first signal that was detected. Maybe the pointer still works. The clicker doesn't, but maybe this guy still works. Yeah, so this was the first signal that was detected. This is noise from the LIGO detector, and then these beautiful 4 cycles. They were detected simultaneously in the 2 sites in the US. And it is really the first direct signal of emerging black hole binaries that we've observed. The revolution didn't end. This is another famous picture in astronomy now. It was the first event detected in both photons and gravitons, if you want. So this was a merger of 2 neutron stars that was localized by the gravitational wave detector in green to this area here. Then the gamma ray telescope pointed to this area, and then all the astronomers in the world were scanning for the right galaxies or so, and found this dot here that was not here before, signaling again the first signal observing 2 messengers of fundamental physics, light and gravity. This is possible. So I'm by far not an experimentalist. I used to break things when I was entering labs as a student, but I'm always mesmerized by the technological. These are really, incredible machines. So the LIGO detectors are 2 L-shaped laser interferometers of 4 kilometers each, and then there's a third machine in Europe, in central Italy. And the technology is just incredible. We are talking about vacuum tubes, multiple suspensions, and so on. It's really a marvel of engineering. So after the first revolution, where do we stand now? So LIGO has collected, LIGO and the Virgo detector as well, they have collected about 700 days of data combined with some engineering periods and upgrades in between. Crucially, some upgrades happen here, which what you see. So this plot is, as a function of the cumulative data taking period, the number of events. Well, what an event is, it's a bit debatable, but the number of, say, interesting things that happen in the detector, and there was clearly a massive thing where there was an a large upgrade to the detector going on at this time. So from the first detection here, we are now at about, maybe this plot is not the latest, the absolute latest, but we are talking about 70 up to 100 events, depending on how you define, so what you call an event or so. About 76 of which are at extremely high significance, say the larger than the nominal 5 sigma, whatever that means. 70 of these are binary black holes, so these are merger of two black holes coming together. A few of them are binary neutron stars, which are interested for all the reasons I was saying before, that there's matter coming in, and so potentially light. One of which has a counterpart. We have a couple of events that are mixed, so a black hole and a neutron star coming together, and even a few that we're not really sure what they are, whether they're black holes or neutron star. One really cool guy, which fully classifies as an intermediate mass black hole, and I'll have a slide on this in a bit. So the fourth observing run of the detector is about to start. They say May 14, 2023. I think it's the latest. And they're going to take 18 months of data straight, meaning that the number of detection will go up to 200, 300, 400 or so in a year times. So that's the typical timescale we are talking about. And I would say the best is yet to come. So this is some prediction that we cooked up a few years ago of the size of the catalog as a function of the, say, calendar year, by guessing what instrumental upgrades we might get. And of course, I mean, the details here are as uncertain as you think they are. But, more or less, we are right here, and we have about 100 detections. We are talking about 1,000 in a few years and millions in a few decades. So that's the typical, big data regime that we expect to enter. I mean, not too far from now, to be fair. And this is just for stellar mass black holes, and there are other bands of the gravitational wave spectrum, namely millihertz waves with LISA, that will be open on a similar timescale. So yeah, I would say the field is entering it's out of its exploratory phase, and we are entering a large statistic regime. What did I do? All right. So what did I want to tell you today? And then I'll explain why I put flowers here. So where do black holes come from? This is one of the holy grail of the field, and why we take this data in the first place. So how do we, once you get one event, not one event, but many events, how do you put them together on a statistical framework? Why I think the data mining tools are promising, and then I'll detail a little bit where we stand, at least our side of the activities of my group, and then we'll move on for lunch. Okay, where do black holes come from? I think the key question here one should ask, from a really almost theoretical standpoint, is, can black holes really make it? Meaning, does it make even sense that we observe merging black holes in the first place? I mean, we do observe them, but does it make sense that, I mean, do we understand why, how, and so they come together? And I mean, the argument here is very simple. If you just take the rate at which the orbital separation, so the distance between two black holes, goes down as a function of time at lowest order in the post-Newtonian expansion. So these are results from the 60s as a textbook results. You then take, take this thing here and do ADTDA. That's a typical timescale. So that's the typical timescale on which gravitational waves dissipate energy and angular momentum to decrease the separation appreciably. This guy scales with the very steep power of the separation, which is, well, good and bad. It's good because it means that when the separation is small enough, gravitational waves are extremely efficient, meaning the binary, it's like if it's in pure vacuum. So we don't care really about what's around. So modeling the signal in LIGO is a relatively clean problem. So it's two black holes in vacuum, which is good. The downside, though, is that this is a big number. So if the separation is large, this timescale becomes very large as well. So you can turn the argument around and ask yourself, okay, what's the typical separation at which the timescale is equal to the entire age of the universe, which is about 10 to the 10 year. You put the number in, and what you find is that for a typical, object of the sizes of what LIGO sees, say 10 solar masses or so, this critical separation is about 10 solar radii, which is small. So typical binary stars, they are at separations which are order of magnitude larger than that. So if you take a binary stars naively as we observe them, and you hope that they will collapse, form black hole, and merge and be observed by LIGO, that's hopeless. It will never happen. It will take more than the entire lifetime of the universe to do it, to produce a single merger. So that means that it's not enough. So gravitational wave dissipation of energy and angular momentum is not enough to explain the data that we observe. You do need something else. You need some astrophysical way of, throwing away energy, get you to the critical separation, this typical length scale, and then from that point on, gravitational wave becomes efficient at driving the dynamics. So conceiving plausible astrophysical mechanism to dissipate enough energy to produce the rate of binary mergers that we observed is a highly, highly non-trivial problem, and is a very open question in the field. I like to, simplify these things to the bone and think about two black holes, like, I don't know, an old couple in their 70s or something, that they ask themselves, have we really been together for so long? And there are two scenarios, I want to say. So the first class of models, you got a binary star. So the two black holes have been known each other since they were little stars. So these are two stars that are born together, same molecular cloud, whatever. They form a binary system like the one we observed. Stars are in binaries, actually. So one star collapses, forms a black hole. The other star collapses, forms a black hole, and that's the binary that you observe. In the other scenario, the two stars, so the two black holes, they've met only recently. So you got two stars, they don't know anything about each other. They're born separately, they're not in binary. Each of them collapses, forms a black hole. And then these black holes live in a dense environment where dynamical interaction are frequent that facilitate the formation of a binary system. Now, to do that, you need a place where collisions become important. And the prototypical system here is a globular cluster, like the ones that we observe in the outskirts of the Milky Way and in other galaxies. So let me go in, I have a couple of slides on each of these just to highlight the complexities of the problem. So this is a typical, so in the first scenario, it's what we call field evolution, because these are binary stars that live in the galactic fields, so not in dense environment. And so it's a non-trivial problem. You need to survive all the stages of stellar evolution to produce a single merger. So you start with a binary on the main sequence. One binary will expand or goes into supergiant, whatever, and will transfer some mass. And this is important to explain then some of the properties that we observe. One guy collapses and forms a black hole. And then here you can imagine the supernova is a pretty disruptive environment, including some dissipation of linear momentum that can kick one of the black hole, ultimately disrupting the binary. So suppose this guy is still a binary and you've survived. Then the next key thing that needs to happen is that the second main sequence star needs to expand into supergiant. And here what we think should happen is a thing called common envelope phase. So basically the hydrogen envelope of this giant becomes as large as the orbital separation of the binary. So you got an helium core and a black hole orbiting within a single hydrogen envelope. And that's crucial to convert the binding energy of the envelope into and shrink the binary separation consequently. So this thing here, which is super highly uncertain, is the critical stage that you need. So if you put the numbers in, you can decrease the separation by a few orders of magnitude, which is the key thing that you need to actually get you to the critical separation I was hinting at before. Okay, suppose that you do it, and one of the problems that you have is that if you shrink it too much, the helium core and the black hole will merge. And so you don't have a binary black hole at the end. So suppose you survive there as well, you got another supernova coming along, right? These core needs to collapse into supernova. If you're still a binary, you maybe form a binary black hole at the end. So in the other family of scenario, we don't do this by stellar evolution, but rather by multiple dynamical encounters between black holes. So the idea is that you have dense stellar clusters where three-body interactions are frequent. And this is some integration by someone. On average, when you scatter a binary against a single object, so if the orbital velocity of the binary is hard, if the binary is hard, meaning the orbital velocity is larger than typical dispersion of the stars of the cluster, the most statistically likely outcome is that tight binaries become tighter. So there are many encounters or so, but at some point one of the three guys goes away, and the final binary is tighter than what the binary was before. So they're not the same black holes anymore, but on average, it's a tighter object. So if you then play the game of actually cooking up an actual model, it's extremely complicated. So this is a specific scenario that was built to explain the very first event. And you see how many and how detailed different interaction and things you need to produce a single black hole merger with the properties that we observe. So it's a highly non-trivial problem. In recent years, though, there was another scenario that was popularized, and I thought I put it here because it might resonate with some of the activities here in the group, which is the formation of black holes, stellar mass black hole embedded in AGN disks. So here the idea is that you have a big black hole, so a supermassive black hole at the center of galaxies, and then you have two tiny black holes like the ones that LIGO observe, forming a binary embedded in the disk. This is analogous to binary planets or so, right, that form in protoplanetary disk. And the key, I'm not too much of an expert here, but the key phenomenon that happens is that the binary forms these wakes that gravitationally, so you basically shed away angular momentum from the binary onto the disk, that shrinking the binary a bit. So that's another potential mechanism to explain, to boost the rates of binary black hole merger. And there are interesting thing called migration traps, where one guy can get stuck in the migration of the disk, and then so another black hole can be, brought to that location, basically. Okay, so this business of formation channels is really an industry in the field. There are tens of papers published each week on this problem. How can we tell them apart? And well, black holes are simple objects, so there aren't that many observables that we can rely on, namely 3 or 4 really, masses. So that's the easiest thing to measure the mass of the black holes. The mass it's to 0th order the length of the signal that we see. So that's an easiest quantity to take out. Early papers were saying that with 100 events, we would have figured out the formation channel problem with the masses alone. And I don't think that's true anymore. So these were somewhat optimistic prediction. And I think the key point here is selection effects from the detector. So this is a prediction from a few years ago. And basically, so this is a field and a cluster model. So the 2 vanilla scenario I was hinting at before. The field lines are the intrinsic population, so what's produced by their models, and the dashed lines are what's observed by the detector. And as you see, that even if the intrinsic population are different, by the time you observe them, they become very similar. So the detector puts a very heavy selection effects on the masses, which tends to wash out some of this difference. So you need a lot of events to actually dig them out. So yes, they're easy to observe, but they're also somewhat weaker observables in some sense because they're heavily selection biased. Eccentricities are promising, though they are hard to see. The eccentricity goes down. So most binaries that we observe will be basically circular. But if even one of them is not, that's really promising because it really means that you need frequent dynamical interaction happening just before the binary enters the LIGO band. Unfortunately, for the 2 main scenarios that I was describing before, eccentricities in the LIGO band are expected to be very low, 10 to the minus 4, 5, 4, 3 if you're super lucky or so. You can come up with other scenarios that boost the eccentricity, namely binaries merging in triple system. It's a promising scenario here. Spins are promising. This is something I worked on in the past. The idea here being that if the black holes have been, growing from binary stars, there are some at least aligning processes that might have aligned the spins, because the 2 things have been born together from the same molecular cloud, so they might inherit the same global angular momentum of the cloud. So to 0th order, you expect binaries that are born in the field to be with spins more or less aligned, while binaries that have met by a dynamical interaction to be with spins more misaligned. The picture here is a bit more complicated because supernova can tilt the spin, even if the system was born in a binary. So this is an actual prediction by my group from a few years ago. And so we try to track the spin direction during the lifetime of the system. And as you see, individual binaries here can actually change their spin orientation quite substantially during the evolution. So yes, it's a cleaner observable compared to the masses, but the modeling side is non-trivial. Okay, so one thing that emerged as a key prediction in more recent years, so if you notice all these things, all the citations here are 20, 17, 16, 18 or so, something that emerged in, the last few years is the occurrences of gaps in the mass spectrum. So this is a plot from a standard stellar evolution code where they have the zero age main sequence mass here on the x-axis and the mass of the compact objects on the y-axis. Oh, sorry, there are no numbers here, but this is about 3 solar masses and this is about 50 solar masses. Okay, sorry, imagine the numbers on the y-axis for me, please. So, okay, as you increase the zero age main sequence mass of the star, so these are single stars, no binaries or so, right? So a single star, what object they produce when they die. As you increase the mass here, these guys, this population here are the neutron stars. So a zero age main sequence mass of 20 solar masses will produce a neutron star of 1.4 solar masses, right? So then there appear to be nothing, at least in some models, and this is the putative lower mass gap between black holes and neutron star. So then there's another population of objects, which are the black holes, going from 5-ish to about 50-ish solar masses. So this number here is about 50. Then, at least for some models, some metallicities or so, there appears to be nothing again. And this area here with no compact objects is what we call the upper mass gap, which is becoming extremely popular and promising to constrain the evolution of binary black holes. And then there might be more black holes at even higher masses, though that's a bit uncertain. So let me try to go a little bit deeper into this upper mass gap. So the physics behind this is the so-called pair instability in supernova explosions. So, okay, this plot here, it's similar but slightly different. So now CO is not compact objects. That's the carbon-oxygen core of the star that is collapsing. And this is the black hole mass that produces at the end, done by some supernova simulations. So this trend here is obvious. So the bigger the mass, the bigger the black hole that you produce. So this is somewhat linear here. And then there's this plateau. So out here at, so say 60 solar masses or so, what happens is that it's this pair instability process. So the temperature of the core is large enough such that photons spontaneously decay into electron-positron pairs. If you spontaneously produce electron-positron pairs, you remove photons from the star, meaning that the radiation pressure support from the star drops. The radiation pressure support drops, the core contracts, the temperature goes up. The temperature goes up, you produce more pairs. So that's a runaway process. So the temperature goes up until you hit the ignition temperature of the oxygen in the core. So it's basically a giant explosion, a giant bomb of oxygen going off, which if the masses are large enough, you destroy the entire star and there's no black hole left behind. At intermediate masses here, there's a transition region, which is the so-called pulsational pair instability, meaning that the temperature goes up a bit, you burn maybe a shell of oxygen, not all of it. That decreases some of this, pressure, decreases the temperature a little bit, so the process can become again. So you burn another bit of oxygen and another bit, and so on. And there are our supernova friends that see this supernova with pulses or so that are interpreted as a telltale of this phenomenon, until the core gets low enough that the instability is suppressed. So for us black hole people, the key prediction that our stellar friends are telling us is that black hole formation should be forbidden for masses above 50-ish or so solar masses. So we shouldn't expect black holes with masses that are much higher than this number. Then you can mess around with stellar evolution, and then people argue whether this is really 50, maybe it's 45, or I can push it to 60 by changing some nuclear reaction rates, whatever. But there's a limit. At some point, this thing won't work anymore. And something I'll try to highlight is whether we can bypass this limit by using black holes instead of stars. So why this is interesting? Because of this guy. So 1905-21 was an event detected on the 21st of May, 2019. These are the signals in the tree detector. The confidence of the signal is extremely high, unquantified number of sigmas. And so this is the data. So this is the posterior of the two masses obtained from the data, which shows that the masses of these two objects are about, well, something like 65 and 85 solar masses, which is right where the stellar physics people have been saying there shouldn't be black holes for years. So what is this? So this event kickstarted a flurry of paper. I don't know how many hundreds of papers have been written on why the masses are that large. One of the key, I would say, one of the leading explanation now is the following. And well, it's something we thought about a few years before this event, and thought, oh, if there's an event that massive, maybe this is what's happening. So it's kind of a prediction. So the scenario here is the following. So suppose here you got stars, they collapse and form a black hole, and they meet in binaries, however they do it, and that's the binary that you observe. Or maybe what you're observing is a second generation object. So there are stars, they collapse, form a black hole. These black holes, now these two guys, they're formed from stars, so they respect the limit. So I don't know, 40 plus 40. They merge. This is an 80 solar mass black holes. And then these guys merge. And that's the event that you see in LIGO. Nothing prevents you from having 80 solar mass black holes if you don't rely on stellar evolution anymore, but rather on a previous generation of black holes, which is very reminiscent to what happens for supermassive black hole formation, right? Where we think that this hierarchical growth, it's at the core of, like, say, large scale structure also. So I like to think this as an orthogonal, because I don't really care how the black holes are put together, just that they do more generation of mergers, but at the same time complementary direction to the field cluster debate I was hinting at before. And I say complementary because, of course, to put together black holes, you need some form of dense environment that brings them together, right? But maybe there's a feature that is the generation itself that can be taken out of the data before we go into the complexity of the astrophysical formation channels. And what I really like about this is that there's a corollary prediction, which is the following, which I call the spin magic number. So, okay, so when you merge two black holes, you have to convert, so you merge two black holes and there's a final black hole at the end. You have to convert the spin of the final black hole is approximately at least the sum of the orbital angular momentum and the spins of the black holes before merger. So at plunge, right before the binary merge. So if the spins are aligned, so L, so this is the orbital angular momentum, and then you got S1 and S2. If the spins are aligned, you got to do L plus S1 plus S2. But there's a phenomenon in black hole dynamics called the orbital hang-up, which was observed in numerical relativity simulations decades ago, where aligned spins, the black hole's orbits are a bit more, so they do a few more orbits before merger. The waveform is a bit longer. So true, you have to do L plus S1 plus S2, but L is a bit shorter because they plunge from inner in. So the orbit is a bit smaller. L is a bit shorter. So it's a sum, but a shorter vector here. Right? If instead the black holes are the spins are anti-aligned, you got to do L minus S1 minus S2, but the binary plunges from afar. So L is a bit longer. So these two effects can kind of counterbalance each other, such that more or less whatever you do when merging two black holes, right? And this is not exact, but it's largely independent of the properties of the incoming binary. The final spin has a distribution that is highly peaked at the characteristic value of 0.7. So it's the result of this orbital hang-up conspiracy. And this is a specific realization of this problem. I started with first generation black holes that are flat in spins, and we try with different, prescription on the masses and so on. And already in a single generation, so just by one generation of merger, the distribution that you get, it's highly peaked at 0.7. So, okay, so we thought, well, if you see a black hole, which has, say, 80 solar masses with the spins of 0.7 coming in, that's a pretty solid telltale that it might be the results of a previous merger, right? And well, when you start thinking about repeated mergers or so, that generated really an explosions of predictions. This is another realization of the same idea. So here it's a bit more sophisticated. We took a blue population, so a first generation population, which is compatible with what LIGO has observed, and we computed their second generations. We basically merged LIGO binaries within themselves. And what happens is that in just one generation, you have binaries that go leak into these upper mass gap above 50 solar masses, and the spin highly concentrates at 0.7 or so. So thinking about in terms of hierarchical mergers allows you to, well, place binaries in the pairing stability mass gap without violating any stellar evolution finding. There's a peculiar spin distribution peaked at 0.7. Then we realized, well, okay, but you need to be a bit more careful here, because if you want, so gravitational wave take away linear momentum, not just energy and angular momentum. So when you merge two black holes, there's some linear momentum that goes away, meaning that the center of mass recoils in the opposite direction. This recoil is imparted ultimately to the final guy. So you got two black holes merging, and the final guy recoils somewhere else. If the recoil is larger than the escape speed of the environment, this black hole won't stay in the cluster to merge again. So yes, you can maybe merge multiple times, but you need to be careful at retaining merger products into the environment and not let them escape. So that puts constraint on the escape speed that you need for these to work. And indeed, the AGN people that pointed out that in their environments, the escape speed is driven by the supermassive black hole at the center, not by the self-gravity of the cluster. And that naturally provides a place where large escape speed and a mechanism, these migration traps to bring binary together, could, point to a large fraction of these black holes actually being of repeated generations. We published on how promising this event could be for another event, 1904-12, which is an asymmetric mass ratio. I would say now is a leading explanation for 1905-21. And then deeper explorations looked into whether there are actually several of these events in the catalogs. Again, you cannot overdo it for a similar reason than what was said before. And then we use it as a prototype for a deep learning pipeline, which is going to be, I'll be talking about now. Yes? Yes, you can. You get the globulars are basically excluded. So the typical kick, so kicks are, it's a velocity, meaning that it's scale free. So typical black hole kicks are of orders of several hundreds of kilometers per second. So in a cluster, you got the escape speed of a globular will be 20, 50 or so, unless the spins are very low. If you fine tune the spins, so if for some reason stars produce very low spinning black hole, at least the first generation is allowed to stay in. Yeah, or nuclear star cluster. Something that has an escape speed of hundreds of kilometers per second rather than tens. Yes.
Can the same principle be applied to lower mass black hole, like to detect a 30-30 solar mass merger with a effective spin of 0.7? Then that could also be.
Yeah, though that's not unique, I would argue, because someone will tell you, well, a star can do it, right? But a star cannot do 80. So it's
and we don't have enough signal in LIGO band to distinguish between.
Well, there are a few papers. Well, ourselves as well, and these are the study before us that tried to take this generation now at a population level. Though that's admittedly, including the results I'm going to present, highly degenerate with a lot of other assumptions. So anyway, this whole business was enough for a review that we wrote on repeated mergers in LIGO. So there's more in there. Okay. So, okay, we got the stage we are at is that we got many events, many of them interesting, and we are interested in inferring the astrophysics underneath. And from a statistical perspective, this is a problem of, it's a population analysis with selection effects, meaning that we observe a few black holes. So this, by the way, this is a picture I took in the British Peak District during lockdown or so. So I still, anyway, so the physics here is that you observe a few mergers with very high significance, but what you care about is the environment that produces the entire population. So, the climate that produces all these flowers in the back that you're not observing. So from a few selected observations, you want to use these to observe a broader population, most of which is unseen, right? So the statistical framework to do this is the so-called hierarchical Bayesian analysis. So, okay, let me explain this equation. So I'm going to call thetas the parameters of the single events. Say, think about the masses, the spins, the redshifts, and so on. So each black hole binary, you observe these things. So if you have 100 events, you have 100 values of the total mass, say. Then the lambdas are the parameters of the populations. So I say, I don't know, the masses in the universe are distributed according to a power law, and I want to estimate the slope of the power law or so, right? But this could be of physical origin, say, I don't know, the common envelope is efficient to 20%, and I want, or 21, and I want to estimate that number there. So ask my data, tell me something about the entire population, not just, so put the events together and tell me something about the entire population. So the formalism is that of an inhomogeneous Poisson process. So let me unpack this for you. So what we want is to infer the properties of the population. Right? I want to constrain my astrophysical model. So I want to infer the lambda given some data that I measured. Let's start from the inside here. So I want to multiply together, because I have many events, the single event likelihood. So this is the thing that is measured for each individual event. So LIGO measure the stretch of data 2 milliseconds with the events, and that's the likelihood of getting that. A black hole of 30 solar masses will produce that stretch of data. I integrate it over the population model. So that's my own assumptions onto the universe, right? So my own stellar physics model. I say, well, given what I think about the universe, I predict these black holes, theta. Then I integrate them over the single event parameters, multiply, because I got many events. Then this factor here takes into account selection effects. So for instance, say that black holes of 5 solar masses are 10 times harder to see than those of 50 solar masses. If I observe one black hole of 50 and one black hole of 5, because one is 10 times harder, I should infer that there are 10 times more in the universe, right? So this thing is embedded into this term here, which is basically I want again, my population, so that the model of what I think about the universe, integrated over the model for the detector. So this P dat here is, my detector has a 10% probability of observing a black hole of 5 solar masses or so, right? So plug it in here, then throw it a prior, because we are Bayesians. And that's the inference that I have to do. Right. Okay. Hopefully that's not too much. Let me know if that's not clear. Okay. So the key assumptions. So what are the key assumptions here? Well, someone say LIGO or so as measured events. So suppose that I have the likelihoods. That's fine. So there are public data sets now and so on, right? So I need to model my detector, P dat. That's what I think the detector does to my data. And then the more accurate I am, the more unbiased my analysis will be. But then the crucial assumption is the population model. So this is a population-dependent analysis, right? Where I infer what are the best model in my family of models that I consider as plausible for the universe. So what is ppop, basically? And well, there are two options, I would say. So option one is take some relatively simple and parameterized functional forms. So a power law plus a Gaussian peak, truncated or binned histograms that can vary in size or so on. Now, the assumed shape can be inspired by physics. So, we know the stars are more or less, so the IMF of star is more or less a power law. So it kind of makes sense to assume that maybe the black holes are a power law as well, and try to estimate whether that's steeper or shallower than that of stars. So crucially, from a computational perspective, though, it means that ppop, it's easy and can be computed at each likelihood evaluation. So each time your stochastic sampling algorithm needs to ask for a value of this posterior, so need to sample this posterior, you need to compute ppop a ton of times, but this is easy. So you just evaluate a power law, whatever, right? So these, option one thing has been, extremely successful, and has been, pushed by many groups, including the entire LIGO collaboration, our own groups, and so on. These are some state-of-the-art results that you get out of this approach. So these are the latest. So using all the events at our disposal so far, the distribution for the primary mass in binaries, their mass ratio, and their spin. And as you see, there are some features that start to emerge. So for instance, a single power law, it's disfavored at super high significance now. We think there's something more interesting going on in, for instance, in the mass distribution. We seems to see that the spins are somewhat low. So there are definitely more low spins here than high spins here. I would say most of the analysis still largely rely on simple parameterized models. There's some very interesting work, and there are lots of citations that I've omitted here, done on the so-called non-parametric inference. So basically the idea being letting the data figure out the best shape they should fit for.
The eccentricity, right?
No, because we don't have measurements of the eccentricity. No.
But you could in principle.
You could. You could put it in. I mean, it goes into the theta. Right now it's not there, but one thing that I like to highlight here, and this approach has been extremely promising, is giving us a lot to think about actually, is that the latest data seems to uncover a mysterious, in my opinion at least, mysterious correlation between the mass ratio and the spin of the binary. So it looks like binaries with higher spins tend to have a more extreme mass ratio, and I think nobody really can explain this or so on. And it seems to be very solid actually. Okay, so option two. So when we were thinking about this a few years ago, I felt like, I don't know, there were the statisticians doing their fancy Bayesian things and so on, and then the astrophysicists putting lots of effort into simulating clusters, AGN, stars, stellar evolution, whatever. So we started to think, okay, can we interpret gravitational wave data using astrophysical predictions directly? So can I feed the data to the simulation, or the simulation to the data straight away without going through parameterized functional forms in between? I mean, nice idea. And you immediately, as soon as you think about it, you immediately enter a key computational problem, namely that evaluating your ppop that goes into the likelihood and so on now is a stellar simulation, is a stellar evolution simulation. So maybe that takes a day to do it, right? If it's a fast code, or maybe a month if it's not, right? So it's hopeless to think that you'll evaluate this population at runtime while you do the inference, right? You need to be doing something else. And this is the enterprise we enter. And I mean, we think that exploiting deep learning tools can provide an answer here, or at least a possibility to tackle this problem. So let me go quickly through the ingredients that you might need to make this work. So you need a stellar physics code, right? I mean, I'm not a stellar physicist, someone writes a code that produces stars given some assumptions onto the universe. Say, if the supernova kicks are 100 kilometers per second, if the efficiency of the common envelope is 23%, whatever, I produce a population of black holes. And there are several of these codes, and now many of them are public, or so they've been developed across the years. Then you design a training bank. So maybe you get this code, look at how many computational hours you have in your clusters, and you decide, well, okay, I can afford 100 simulations. Where should I place them? And this is a non-trivial problem if you then want to have good inference down the line. And what we find being extremely successful is this thing called space filling algorithms, which are techniques to place, it's called simulation design inference. These are techniques to place training points covering the space as much as possible according to some metric. We've been using something called Latin hypercubes, which, funnily enough, is the same thing that they used to build the Sudoku puzzle. You know, the Sudoku puzzle, they don't have all the numbers on one side, because there you cannot, I mean, that it's not fun enough, right? So they distribute them, evenly enough. And they do this with this algorithm as well. I find it very funny. Okay, so you design a training bank. You are likely going to need some form of data compression for what comes later. So you cannot possibly parse all the outputs of these simulation. And we've used principal component analysis quite successfully here. And we are messing around with nonlinear dimensionality reduction now, though this is, well, it's not working, but maybe it will work one day. Then point 4, you need a conditional density estimation scheme. So given a numerical set of lambdas, you want to estimate, this is a density problem, right? You want to estimate the probability of having theta given the lambda. So basically, you have a set. So for each fixed lambda, so you have 10 simulated universe from your stellar physics code, which could be this blue distribution here. You want to estimate, you want this function here that continuously maps the thetas into the lambdas into the thetas, right? So basically, you want an emulator that emulates what a simulation will look like without doing it, right? Which is a typical machine learning problem. So we've used Gaussian process regression in the past, though quickly realized that it doesn't scale well. The matrices that you have to invert that get too big too quickly. What I'm going to present today is a combination of an FFT-based kernel density estimation and a neural network. Another group has been using autoregressive flows quite successfully, and we are exploring what's better and what works and what doesn't. With autoregressive flows are another flavor of deep learning. Then point 5, you need a model for the detector. Someone needs to tell you this pdet. That's crucial for an unbiased inference. We've been doing with simple SNR cuts. That's the easiest thing you can do. The field is moving along and using actual pipeline injection. So putting fake data into the same pipelines that then you would use when you do the real analysis, which is arguably more accurate, though it adds complexity and cost to the inference runs. There have been, including one by myself, some attempts at tackle the modeling of the detector with machine learning as well. Point 6, you need a sampler. So you need to, when you have all the ingredients, you need to sample this posterior. And for now, we are just using a simple nested sampling, though who knows whether there's something else around. And then the data. That's what, the key players here remains the data, which is something that looks like this. Okay, so we have this idea. We want to prototype the entire business. And we are doing this with exploiting these hierarchical black hole mergers I was explaining before. So the idea is to take a parameterized model, so much like LIGO does or so, but allow for hierarchical mergers. This is good at this testing stage because on the one hand, the simulations are quick and easy. So, we wrote the code to do it and it was cheap enough. But at the same time, the population becomes non-analytic. So it's a stress test for these kind of models. So what I'm going to do is that I take a cluster, quoted, which has nothing to do with dynamics or so. It's just a collection of black holes with a single parameter that is the escape speed. I generate masses according to a power law, spin according to a flat distribution between something and something else. I pair two black holes, so I select two black holes randomly from the cluster with other power laws, and I distribute the escape speed of the cluster with yet another power law. So
you can't have people interaction.
No, easier than that. So this is a population that has 6 free parameters that I then ask my data to tell me their best combination of. All right. So in a nutshell, the evolutionary scheme is super simple. You have a collection of black holes. You pick 2 of them at random. These things will merge, produce gravitational waves, or record this signal in your event files or so on. They form a final black hole. If the kick that this black hole receives is larger than the escape speed, I take it out. Otherwise, I put it back and I iterate until the cluster is all gone. Right? So it's a simple prescription that mimics some of these hierarchical merger formation scenario, though with a very easy to test, train, more simulation, fewer simulation, different designs, and so on. So these are kind of some of the populations that you expect. So this is the Chern mass and the mass ratio of the 2 black holes, and that's 2 spin parameters. And these are 4 representative locations in the parameter space, right? With no particular, we just pick 4 simulations and look at what they are. And so there are multiple peaks. These things are all correlated. There are spikes. You see how sharp this feature is, and so on. There are degeneracies between the parameters. So what I want to say is that it's a complicated problem. So fitting this thing, it's a hard problem. It's not a smooth distribution that you throw a few points and the fit is accurate enough. So it's a hard problem, which is precisely what we want. Sorry.
So the escape velocity is updating every time.
No, it's not. It's a fixed preparameter. No, it's a fixed preparameter. Each cluster has a different one. Yeah, it's easier than that. It should, but no. Okay, so here is how our current pipeline looks like. So you start from here. You have your universe that you imagine what the universe. We see this simple cluster thing. We run the simulations, and we get the parameters of these of all the black holes. So we have catalogs of black holes for each of our fictional universe. Then let's go down in 3 parallel strands. So this is the actual population model. So given this set of simulated number, we want for each simulation to construct their density profile, so P of theta, and that's done with kernel density estimation. This gives us the probability evaluated though at the individual location where I've performed my simulation. The deep learning model takes care of the density estimation, of the conditional density estimation, basically interpolates. So the KDE smoothens over theta, and then the deep learning interpolates over lambda. Then go down this way. For each of these simulated black holes, we estimate how likely they are to be detected. We got this sigma factor that is something that was entering the likelihood a few slides ago. And another deep learning pipeline will estimate the selection function. And this is which is unique to something that you can do with this model, is you can keep track of subchannels. So if in your catalogs you have that some black holes are formed one way and others are formed other ways, say in my case could be the generations of the black holes, which I can easily keep track, but it's far more general than that. Say you have an AGN simulation, you can estimate whether the black holes were formed in the disk or outside of the disk. So this gives you an handle not just on the formation channel you're simulating, but on subchannels, which is something completely unique to this pipeline that is never, well, it's not in the radar of people at least. So if you keep track of where your black holes are coming from, yet another deep learning tool can estimate, can interpolate the branching fractions. All these things go together, the data goes in. This is your nested sampling step, and hopefully you get some astrophysics out at the end. Okay, so this is how the population neural network looks like. So it's a fully connected network with whatever five inner layer and a total of about 70K parameters that we need to optimize. It's not even that crazy. I mean, it's a TensorFlow model that takes a few days of training time on a single GPU. So it's not that bad. And it's an offline cost. You have to do it only once. So it's a decent problem. So this is a typical machine learning plot. That's the loss function, how the loss function goes down as the function of the epoch, meaning the number of times the network has seen the same batch of data. And the fact that the training set and the validation set is sufficiently similar, it means that we don't have significant overfitting. We quantify this in terms of the so-called Hellinger distance, which is a measurement of distance between probability distributions, showing that indeed training and validation, they return statistically equivalent results. So these are some of our interpolation results. So again, these are 3 locations in the parameter space. The points are the validation simulation, and the line are the prediction from our network. And as you see, we can capture these multimodalities and sharp features also extremely well. The blue distribution is the absolute worst in the entire training set, in the entire validation set. It's probably this point here, where we do miss some details, but again, given that this is the absolute worst over thousands of simulations, we're pretty happy with these results and decided to proceed with the inference, which is this mega plot here. So this is the full thing. So given all the gravitational wave data that we've observed, we fitted for 4 events parameter, 2 masses and 2 spins for each of the events, and a population model that has 6 free parameters, all of them correlated in a nasty fashion. So this is a complicated problem, maybe one of the most complicated population analysis that was done in the context. And this is in Bayesian terms, this is the corner plot of the 6 population parameters. So with the error bars, we highlight, preferred location in each of these parameters. That basically this is what, given this model for the universe, the data is telling me that this specific location is preferred over the other. That's precisely the game of the population, of a population analysis. It's coming from, this is more than what's been done before, but still not too much that we can train the thing on a meaningful timescale. I think 6 correlated parameters was the first analysis that was done. So it's more than before, but no, 1,000. Yeah, I mean, we cannot do that yet, right? And or understand what's happening and make sure that the sampling converges and so on. And the neural network does what it's supposed to be doing and so on. So
can you tell us what kind of parameters also we included? What are the important population parameters which you kind of didn't include now, or which can be included in the future?
Well, this is just a prototype, right? I mean, you'll want to do it on a real stellar simulations, right? Where the parameters then become things that are much closer to the astrophysics, say the strength of supernova kicks, the interaction, the winds in massive stars, and these kind of things, right? This is a prototype stage, but at least we show that. I mean, the populations that we have underneath. So where were they? So these guys, they are of similar complexities to what the stellar physics people predict. So at least the data complexity of the problem is sufficiently similar, I want to say. Okay, so let me go on. All right, so let's go a little bit deeper. So let's try to unpack these predictions. So this is the mass spectrum that we predict. And then the nice thing is that we can, because we have these, we can keep track of the different generations of mergers. So the entire mass spectrum that we predict is this blue line, which is not dissimilar from what the LIGO people have found before, right? I mean, that's the mass distribution of black holes that we see. Funny enough, we seem to see some structure in the gap. So above 50-ish or so solar masses, that is these additional generations, though it's within the error bar, so don't claim anything. What is really nice, I think, is that within this approach, because we have the distinctions between the generation, we can then see, okay, if I only look at first generation black holes, what are their masses? And I found the purple line. So if you allow for multiple generations to be there, and remember the maximum mass is a free parameter. So this thing could be 100, right? Or so. If you allow for this to happen, the fit wants to fit this part of the population with first generation black hole. And then when the rate goes down enough, it places higher generation things, which is nice, I think, right? So if you are even in this relatively flexible model, you seem to find that the low mass part is fitted by first generation black hole, and then the high mass part is fitted by higher generation black holes with the cutoff that is 40, 35. I mean, given how simple this model is, I really like this when I saw this plot, right? So for the spin dynamics, well, we have some fat, because this hierarchical generation gives you spins of 0.7. In terms of this effective combination of the spins, this translates into fat tails at large values. Again, something that is within the error bar, but some of the spin dynamics seems to suggest that at high spins, which is precisely where this hierarchical thing is supposed to be important, there are hints of structures or so, though the error bars are what they are. But spins are hard to measure, and we knew this. So crucially, one of the nice things is that, so I'm not inferring the escape speed here of the cluster. What I'm inferring is one of these power law, which is the power law of the escape speed. So if you want, the escape speed is a secondary population parameter, which is not tackled in the inference, but some of the parameters are related to it, right? And this formalism, nature allows you to go back to secondary population parameters. So here we plot the distribution of escape speed that we get from our simulations, which again, the model is too simple, so I wouldn't look too much into this line. But it's nice that this going back to secondary population parameter, I think it's extremely promising. So say, for instance, you want to estimate the metallicity of the environment. The real environment will have all sorts of metallicities in, right? But you can pinpoint which black hole comes from which metallicity in a statistical sense, which I think it's nice. And then the other promising thing is this thing about subchannels or so, right? That you can keep track of different subset of your population and fit for the branching function as well. So we've applied it to generations of black holes. And what we find is that the fraction of black holes that are of first generation has this posterior distribution, which is peaked at about 75%, which is compatible with what other papers seem to find in other contexts. So saying that, I mean, it's a very model-dependent measurement because there are a ton of assumptions that go in, but it says that if you allow for repeated mergers to be there, the fit does want to put, the fit wants them, right? They help the fit to explain the data a bit better. So don't take this number too seriously, but this is not 100%, I think. Okay. And this is it, really. I'm almost done. I'm basically done. So I think we're ready to go, I like to say. So we have a complete and optimized population inference pipelines, which is in our dreams at least, supposed to digest outputs from astrophysical simulation and feed them directly against gravitational wave data without relying on functional forms in between. We've applied it to hierarchical merges and highlight that some of the features that people have been overlooked or so can actually be taken out. I think the deep learning is crucial. I don't see another way of doing it. The astrophysics that we have is, well, too simple, right? It's a power law, it's a cooked up power law, basically. But I think we are ready to move on and do this on state-of-the-art models. And that's all I wanted to say. I'll take 1 second to for a shameless advertisement. We are organizing a conference on gravitational wave population. It's going to be a large workshop, about 100 participants. It's going to be in Milan in July. So if you are interested in these things in any form, give us a call. Okay, thanks. Actually, I'll leave this out during the question.
I mean, this pipeline is obviously very cool, but I wonder if, or what you think about, you know, if you want to take some population model and then train this neural nets to interpolate, will you not just inherit all of the weird quirks of that specific population model? And maybe in some sense, just relying on functional forms is better in that sense. Like, why is attaching this pipeline to a specific code better than using some generic functional forms? Will you not just inherit all the problems of that specific?
Yes,
model?
I think so. An interpolator is never better than what you interpolate. That's certainly true. So if you fit a shitty model, your result is going to be shit. So I'm on YouTube. Sorry. Sorry. Sorry, guys. I forgot about this. I'm sorry. So yeah, if you fit them, if you have a model that's not too good, your results won't be good either. I don't think that functional forms are useless. Absolutely. They've been teaching a lot of stuff. For instance, this correlation between spins and mass ratio, it's something that has been highlighted with just putting 3 Gaussians on top of each other. And I think it's really promising. I do think, though, that these functional forms are, they want to be flexible, but they're really not, because again, the pairing stability people say that there's a pile up. Okay, let's put a Gaussian peak there and let's see what happens, or so on, right? So I do think there's a value in try and go closer to the physical parameters, right? Again, common envelope and all the things within some assumption. I mean, it's always going to be a model dependent, but I guess all physical inference is model dependent, right? You're testing a theory always, right? So, and I think the two things should go hand in hand and help each other, I think.
I would say that maybe it's the population synthesis models that are not ready for this pipeline, if you catch my drift.
Oh, go tell them. I mean, go tell them and tell them to give me a better code, and I'll run it. I mean,
in principle, just very quickly to follow up. In principle, you could use the same pipeline to feed the results of 2 very different types of simulations, right?
An estimate. Yeah, that's actually
2 or more, 2 just to say the minimum.
Yeah, it could be. So this is one of the other things that we have in the pipeline, which not in this pipeline, in the pipeline of things that we'd like to do is to look into population systematics. So if you think about the single event inference, this is something that, the LIGO people do all the time. They feed their data with different waveforms and they check whether the results agree with each other. Sometimes they do. If the binary parameters are, high mass ratio, high spin, or complicated things to model, sometimes they don't, and they quote it as a systematic error. So all the posteriors I have, these are statistical errors. But then there are the systematics errors. So for instance, this beast here would allow you to apply to 2 population synthesis code that are supposed to model the same physics, but in reality they don't, because different developers have made different choices, and let you estimate systematics at the population level, which is something new, I think.
Okay.
For instance.
More questions? Joseph?
Maybe I have a question. If you could help me understand. So we were showing this procedure when you have a cluster of like nodes, always selecting random couple of these and then merging them and either excluding them from the cluster or putting them back. So
This guy, yeah.
So I don't understand here, because in principle, cannot it happen that you will get like a physical end product of this procedure, even though you are selecting some random couple, which is not what happens in reality. Like you don't create a black hole from randomly selecting those that are on the opposite side of the cluster or something.
Yeah, so this is again, it's a simple model, though it's somewhat in these parameters. So what we do is that, so in a real cluster, you would think there's mass segregation. So everything sinks at the center and they're more likely to merge with each other. So a big guy is more likely to meet another big guy, right? So we try to capture it with these parameters here. So this is the pairing probability. So these are two power law that tells you I don't pick the two black holes at random from my cluster, but I select them according to this guy here. So for instance, if beta is very, very large, it means that once I have M1, M2 needs to be almost the same. So a very mass segregated cluster would correspond to a beta that is 10 or so, very, very large. And these parameters then are allowed to vary and fitted by the data. So these partially address this, though in a very simplified form. I mean, mass segregation is way more complicated than two numbers, right? Based on these things, and these numbers here then are estimated from the data, right? I ask my data to tell me the properties of the cluster, right? Within some prior bounds and so on, but yeah. Yes. 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 Yeah, and I think we have a prior bound that's somewhere here or so, right? Well, this basically means that it's unconstrained. Basically, once the escape speed is, so kicks are okay. This is explaining it. So if you typical black hole kicks are peaked at about 100-ish or so kilometers per second. They have a tail that goes up to a few thousands or so, and then they go to zero. So it's an escape speed larger than all escape speeds larger than 1,000. They're all the same because you retain everything, right? So there's no distinction in these models. There's no distinction. But I mean, 1,000 is a galaxy, right? The escape speed of Milky Way is what? 700, 1,000 kilometers per second, give or take. Okay. So you're already at galaxy level clusters here, right? So this is the distribution of kicks. This is the distribution of kicks. So the fact that so most kicks are about 100-ish or so kilometers per second, which means that if your escape is lower, you retain the cluster, you retain the black holes, and that's why this thing peaks up here, right? But then at some point, this thing flattens because of this, because all the clusters are all the same, essentially. This model is too simple for that. You need more, right? You need to put more physics into this. This was to showcase that you can take out something like the escape speed, which is a population property that we are not modeling directly, which is interesting, I think. Yeah, we try with these bands, right? Globulars go all the way to here. Yeah.
For the goal.
Yeah, you don't need a fancy deep learning pipeline for this. You just need to say that typical kicks are of order hundreds of kilometers per second, and globulars are less than that in escape speed. Yeah, for that, that's a simple argument. That's a simpler argument, I think. No, what did I do? Sorry, I was in the code. Did I? Okay, here, and here. What? I'm sorry, there's some black magic. What's happening? I mean, I hit play and then I don't know. I'll do it from here. I'll do it from here. Because it's the last slide and not the first slide. I'm sorry, guys. I put the title at the end. Okay. So this one you wanted. There's no escape speed here. There's no escape speed here. Yes, which is this gamma here. So this thing here, that's the, so the escape speeds are distributed according to a power law, which is center, which has a posterior, the spectral index of the power law is a posterior that is centered at minus 0.3. So that's okay. That's what I was trying to explain. So you got the gamma is your population parameter, but then if you want to connect it, you need to go back to the escape speed, which is a secondary population. It's what I call the secondary population parameter, which is precisely this plot here. So this line here translates the gamma posterior into the escape speed posterior. This blue line here, right? Which you can, that's the thing that you can compare with the typical kicks, some astrophysics that we try to put with bands and stuff. So this was to say, even if my population parameters looks as abstract as they look, this thing allows you to go back, right? Even if, you know, the stellar physicist modeler has decided that they want to, one flag in their code is the whatever rate of something that I don't know how to parse or so, you can go back to say the metallicity of the environment, and maybe something that you might want to look at, right? It was an idea to showcase this potential application more than looking into the escape speed of clusters, really.
You showed the result of cluster, but how does it make sense to also do similar calculation for a disk, like in an Asian disk?
If you have a population, yes, absolutely.
And also for to go from stellar mass black hole to more massive black hole in galaxy or something, does it make sense to do that for them also, because you will have more mass but more escape velocity and more possibility of.
Well, so this is a population business, so it makes sense if you have many events. So if Lisa gives me 100 of supermassive black holes, yes, absolutely. If it gives me one, not really, right? This is a framework to put many events together. You need many events in the first place to make it. Otherwise, the lower the number of events, the more similar the posterior will be to the prior. So you get what you put in, basically. Garbage in, garbage out. Right.
Oh, yeah, sorry, I have a basic question. And that's about the physical mechanism. So you said you're enable multiple generations of mergers, right? For the black holes. So at the beginning, you said you need to have them very close for the gravitational waves to actually be done. This is always the same mechanism that makes them. How do they lose that basically if you have like one merger?
Repeated encounters. So it's either go back. So it's either something like this, where you imagine these things are black holes, right? That they meet many times or so on. At some point, two of them merge. There's a product that does not get ejected from the cluster, it stays in, and it keeps on going through these multiple encounters. At some point, meets another guy and merges again. So this is one option to do it. The problem here is the escape speed of the cluster, in my opinion. That in order for the black hole to stay in, you don't want to kick him out. Another scenario would be to do it this way, where you have a binary embedded in a disk, they merge, and they stay there orbiting a disk. Then another black hole gets captured by the disk. It moves to the same location, this migration traps thing, and then they meet. Now, at that point, the guy that was there before, it's the product of a merger, and then he meets another guy. So this generation thing does not take away the problem of putting the black holes together. It's just that if you put them together and you do it with generations, that gives you some observables. If that makes sense.
Yeah. So in a way, it's not a specific astrophysical model, right? It's just a specific.
No, but that's why it's clean. That's why it's relatively clean, right? Yes.
It's a good feature, right? Yeah.
It's that this spin thing that goes to 0.7, it makes it relatively clean.
So this the reason why you need deep learning, it's purely a computational constraint problem, right? Okay.
Yeah.
Okay.
I mean, I personally think that if you can do things in a simple way, you should do that. You use complexity when you need it, not for the sake of it. Right?
Okay. So, there you go. So,
Question, maybe on the very first slide you presented, and
Very first. This one,
When you showed that there are basically two channels to create the black hole binary, right?
this guy.
This one.
Okay.
And is there any constraint on, or maybe it's not important at all, when you are already in a binary, so the first scenario, and the star goes supernovae, and you form black hole, is there a constraint on how this star should be to avoid disrupting the binary?
Yes, I think the big constraint here is the kick that the thing will so the supernova, the neutrino emission during the supernova explosion, it's asymmetric to some extent. So you are shedding away, again, linear momentum in some direction, meaning that the black hole or the neutron star that you form receives a kick. So it recoils. If you are in a binary, if this kick is larger than, well, depends on the orientation, but to 0th order, if it's larger than the orbital velocity, you disrupt the binary. The binary is gone, so that everything stops here, and you don't go on forming a black hole. So you better make sure that you survive the kicks. So actually, if you do this for real, most of the rate goes away for supernova kicks. So the vast majority of binary stars will not form black hole because they're disrupted here. Even before going into the common envelope and the complicated thing, you need to survive the first explosion. And that is critical. Surviving the second explosion, it's easier. And the reason is that it's past common envelope, meaning at this stage, the orbital separation is much smaller because you've gone through the common envelope already. The orbital velocity goes as the 1/√, of the separation. So for the same kick, it's easier to survive here than here.
Okay. So, no more questions. Thanks again.
Welcome.